Okay, all. I hope it says I'm live, so hopefully I'm live. Everybody let me know if you see me, hear me, and everything is good. Welcome, welcome, welcome. Happy Field Day. Well, coming up, right? So everybody who's on this feed, this is my Patreon family as well as, oh good, I see people putting their thumbs up and hearts and stuff like that. Everybody who is on this feed, actually the whole reason why this forecast was inspired was really my Patreon community. I have to thank them for it. And because I ended up doing for Coffee and Ham Radio, I did an interview with them just the other day, and I was talking about doing a forecast, and they were mentioning, oh my goodness, I was seeing a lot of people in the chat saying, please, do this live for us. We would love to see that. That would be so important and so fantastic. So I said, well, let's just do it live for everybody. So if you happen to just be tuning in on YouTube, this is the first time I've ever scheduled something in advance on YouTube. Usually I just do that for my Patreon community. So you have them to thank and their generosity to thank for why you got advance notice of this field day forecast. And also thanks to Bart and Jerry and Mike and who else was talking to me? Chris. All of you guys on Patreon have inspired some of the material we're going to talk about today. Because this will be first a forecast, and then I'll go into a little bit about MUF, FOF2, and believe it or not, how to read ionosons. So it's going to be really simple. I'm going to break it down into easy stuff because otherwise, it can get really complicated. And this isn't a physics lesson, and it's not really a mini course. But I am, for those of you who are really interested in field day and really want to understand a little bit more about how you can use these charts to better, to better understand what your conditions are and possibly make more contacts or know where to make contacts. I'm going to try to help as best I can. So that being said, my favorite ionoson site is down today. I don't know why, but it's down today. It's so frustrating. There's actually 2 sites that are down, and they've been down since last night. And I'm like, luckily ionoson data can be found in many places, so I have some backups. So I will show you. That. You'll see all those skeletons here in a minute. And I'll show you what the site normally looks like, or the type of data you can normally get from that site, because I have an archived bit of it. So we will go into that at the very end when we start talking about ionosons. Okay, so thank you, Mike, for being here. Thank you, Jerry. Those two, you'll see Michael Richardson and Jerry Ryan. Both of those two are amateur radio operators and VIPs in my Patreon community, and they are the moderators. And also, if you end up seeing Nick Gaspard or Chris, good, Chris is here. Those people are also VIPs, so be very nice to them. They are not moderators yet, but they may. Nick actually has offered, so be nice to them now because they have a straight line to me, and they will also pay attention to what is being said and make sure everybody is playing nice, all for field day. Okay, good. Glad everybody can see me and hear me. And got a crazy echo going. Do I have a crazy echo? Is everybody hearing a weird thing? Tell me if my audio sounds echoey or if it sounds good, because I'll troubleshoot. I'm waiting because I don't want it to be hard on your ears. Oh, echo was me. Okay, good. Wonderful. Okay, thank you. Yeah, we'll see. I have, one woman show here, so usually the tech issues are my fault. So, all right. So let's start off. We have a very interesting sun. There's been a lot of changes over the last couple days. I'm sure some of you who pay attention to the sun wonder why it's not letting me zoom out. Those of you who've paid attention to the sun probably have been following along. I know some of you are very much into this. And yeah, I guess I'll start on this side. And I've got it's mirrored for me again, and it's so frustrating when it's mirrored because it makes me think backwards. So as you can see, if we're on, this is not working for me. Let me do it on this side because I'll feel a little bit better. Here's the east limb, And you can see there are 2 new regions that are rotating. Actually, there's more than that. There's like 4 different regions that are rotating into Earth view over the past couple days. Sadly, the regions here that are returning, these were ones that gave us some really nice stuff last time they had rotated in view, and they were firing off some really nice fireworks on the sun's far side. Sadly, you'll see it right here around the 22nd or 23rd. You'll see the one in the north fire off a really big solar storm. It'll happen. There it goes. And oh man, I was so upset when I saw that, because that was a big monster. And with these early sunspots, these early active regions in solar cycle 25, when they blow that large, they're basically done. That's it. They're done. They're done, and there's nothing left of them. And sure enough, as it continued to rotate into Earth view, they're not even sunspots anymore. They're just plages. So we're getting some remnant solar flux from them, which is good, but don't expect any big solar flares from this region. Don't expect any more solar storms from this region. I think the regions are basically kaput. And will just continue to fizzle over time. But that's nice. That's good news for field day, because that means no radio blackouts from these regions. When we were worried when they were on the sun's far side if they could come in and become flare players. Doesn't look like it. However, the southern hemisphere is a different story. We have this one region that is rotated into view. It's starting to rotate into view right here, right around the 23rd. That region, this is taking so long. Come on. It rotates in. That region actually is not that big a deal, but then there's one just behind it, and you're beginning to see the fuzz of it behind the limb right there. See that right there? That region has grown very rapidly. It's still growing. It's now been numbered region 2835, I believe, just over the past day. It's been numbered, and it's not the only region. We have more regions on the sun's far side, but that region is the one we're watching very closely, because as it continues to grow quickly, that means it could become a flare player. Is it a flare player yet? Not. It doesn't look like it is as of yet, but we'll get into that more in a minute, because I've got a different image. I've got the HMI images up, so we'll look at the magnetic configuration of these regions here soon, and we'll talk about that. Meanwhile, we actually have had yet another flare, and I don't think it was from this region. I haven't taken the time to identify it yet in the database, because I don't really see it. I don't really see the source of it. It was a small C-class flare today, but I don't really see the source of it. It might have been from this region here as it begins to rotate. This is old region 2833. As it's rotating off of the west limb, it does fire off something today, but it's really pretty much on the sun's far side right there. So I think that might have been the very small C-class flare that we saw today, which means that is going to go kaput. So if anyone's been looking at the X-ray flux and they see, oh goodness, we're seeing flare activity. Okay, yes, but that may be just from this region and not from the new region that's in the south. But so at least the regions that have been playing flare have quieted down. They've been in the north, both this side and this side. They have quieted down, but we do have this new one that is not a flare player yet, but it's thinking about it. Okay, so that's really the situation on the Earth-facing disk in terms of active regions, right? And as far as solar flux, and we'll take a look at solar flux here in a minute, a little bit more closely. But the active region part, we're actually sitting around the low 80s right now for solar flux, but that is going to creep up, and I'll show you why in a few minutes. Meanwhile, let's talk a little bit about geomagnetic storm stuff, right? This is stuff that transients, the stuff that blows off of the sun. Sorry for the jargon. I forget I'm not in a mini course, so I start throwing jargon in there. Solar storms, that's what I mean to say. Sorry about that. Okay, so what we're talking about that we're just kind of getting through, we're finishing getting through, is just a remnant coronal hole. That's a polar northern coronal hole that kind of came down and gave us a little bit of fast wind. That has settled down. It really wasn't all that strong. We've seen a little bit of activity at high latitudes, which is beginning to settle. And the nice thing is, I think we're done for like maybe a week. There's like nothing on this Earth-facing disk in terms of coronal holes other than this puny little guy in about mid-disk right here, back on the 22nd. That tiny thing may give us a tiny bit of activity at high latitudes in, or I don't know, maybe 2 or 3 days-ish, give or take an ish. But it's not even going to be noticeable to us at mid-latitudes for the most part So if you're doing mid-latitude for field day, you're in the clear, and there's nothing, excuse me, nothing else going on until we get to this other region that, whoops, it just disappeared on me. We do have another coronal hole that's going to be rotating into or strike zone, but that's not going to happen for easily 5 days or more. So for field day, everything is cool when it comes to the solar wind, right? We're going to be just kind of stumbling and bumbling along, and I'll show you the 5 day in a second. The nice thing, one thing that we had been watching, and you can't really see it in this wavelength, it's up over here. It's right in here. This is a filament. Now you can't see it in this wavelength. This is why scientists look at things in so many different wavelengths. So if we flip over to 304 angstrom, I don't know if I mentioned that one filament that we had been watching. Remember in my last forecast? Well, here it is. Look how pretty it is. Looks like a big rainbow bridge, except it's all red. But it did finally kind of erupt, but not with any force. That region, or that filament, as it erupted, kind of like, it looks like most of it fell back to Earth. Or it fell back to Earth. It's like the man who fell to Earth. No, it fell back to the sun. It's like the time I called this a planet. Where's my mind today? I don't know. So the most of that filament fell back to the sun. So we don't really have a solar storm. We don't have to worry about an Earth-directed anything. It just wasn't enough to give this, have this thing actually launch into our faces. And I forgot to mention, I probably have it up somewhere. Do I have it up? I don't know if I have it up. Let me pull it up for just a sec, just for fun. Let me pull up yeah, here we go. Oh, good, it's still up. Okay, so just so that you can check, because we're talking a bit about solar storms at the moment. The only solar storm that we have coming from the sun right now. Now, let me preface this. This is Enlil. This is a model. Okay, it's not real data. This is NASA's version of the model, and it's a solar storm prediction model. So what we're doing is we're looking down at the sun. For those who are not initiated, we're looking down at the sun from the North Pole, and Earth is the yellow circle off to the right about here. Okay, that's Earth. So this thing, whoosh, this big banana thing that kind of whooshed out on the sun like that, this was from that East Limb eruption, that big blast that we saw that took out that one active region that I was hoping was going to give us a little bit more activity, completely took it out. This is the big solar storm that was launched. And as you can see, it's pretty big. So it's going to have a lot of fun over here on the east, way east of Earth. Sadly, it's not going to hit us. I mean, maybe not so sad because it's field day. You guys don't want a solar storm to hit us. But aurora photographers right now are crying. And I feel badly for them because they haven't had any good aurora in a while. So outside of that, we don't even have, if you look at Earth over the next few days, we really don't have any big, fast solar wind pinwheel things coming at us either. It's kind of just a soft mush. And that's really what's going to continue. So through field day, the solar wind really is going to look pretty good. There's just not much going on. So I wanted to show you that. And that filament eruption really didn't add to the mix at all. So as pretty as that filament eruption is, as we take a look at it, there's just not much there to really erupt. It all just kind of fell back down. So hopefully that takes care of any questions there. And then, of course, we do have a couple other filaments that we're paying attention to as the solar cycle does ramp up. We are having to watch for filaments more often. There's even one in the Earth strike zone right now, but it doesn't look like it's really going to do anything. So we're just kind of keeping an eye on it, but everything looks pretty quiescent, pretty quiet right now. Now I'm going to get to the magnetic field, but before I do that, I'll stop. Since this is an informal forecast, I will stop and see what kind of questions anyone might have. Does anybody have any questions for me at the moment? Or anybody not understand what I've gone through thus far? Hey, Andy, good to see you here. Finally, the filament has launched. Yes. I'm buffering so badly I can't watch. Will this remain on here after the live feed? Yes. Dolissa, yes, it will. I will not take this down. So this will be an informal forecast forever. So, hey, Tamitha, so is the sun white and brighter now than 20 years ago before I remember more yellow sun? What's causing that? I would imagine that's more a terrestrial thing than a solar thing. our sun is still pretty weak when it comes to the magnetic field strength, and so that means actually the total solar radiance is down a little bit. So even in visible range, it's not as bright. So what you're dealing with is probably more of an atmospheric effect, believe it or not. And that's about all I can say about that, because it could be a whole host of things. There's a long way from the sun to the earth, and the sun's light has to get through all of it. So there could be so many things that happens. Okay, solar wind, not a problem. You are correct, Freeman. I mean, chosen one. Sorry about that. Okay, so we're good here. What is the situation with the Saharan dust all over the north and south? I know. Oh my goodness, I have no idea if that's going to affect field day, and I have not looked at over the past 24 hours. I have not looked at the most recent imagery, but that dust is coming, and I know it affects Puerto Rico. So if you guys happen to be, talking to, if you're in Europe or something, and you're seeing some of that stuff coming over up from the south, or if you happen to be on the east coast of the United States, you may get something. And how that affects radio propagation, I don't know, but I do know it affects it. Sadly, I'm not very good with neutral dust. That's an area I have yet to learn. But yes, be aware of that, that yes, we do have a dust storm coming, and it is very visible on satellite imagery. So I have been told in the past that it affects VHF frequencies much more readily than it affects HF, but I don't have more than anecdotal evidence for that, because I just haven't taken the time, and I haven't had the time to dig into that side of how things work. But yes, be aware there is a Saharan dust event happening that's pretty intense right now, and it's coming. It's still coming. How does the chemistry of the sun affect space weather? Oh my goodness, that's not something I can unpack right now. There's so much of that, and a lot of that is in my space weather mini courses. But the chemistry of the sun is, it's a plasma, so the chemistry is very specific. It's more like high energy physics at that point, because chemistry is far more about atoms that aren't even neutral. So it's not neutral chemistry that we're talking about. It would be charged chemistry, which has a lot more to do with electric and magnetic fields than it does in just normal chemistry, like in neutral environments. Yeah, our atmosphere is likely not the same as it was 50 years ago. Okay. Oh, right. Yes. Okay. That's a good thing. And that's going to get me back on track. So PE1, PME. Yes. We had SFI over 100 the other day. I will talk about that. That's going to come up. So let me get back to this. So what I wanted to show you, for those of you who are asking, and I'm surprised I didn't get a question on this. A lot of people keep asking, where are we in solar cycle 25? Are we there yet? And I hate to say it, no, for those who know what the terminator is, no, we have not passed the terminator yet. And I just had a talk with Scott McIntosh just the other day on this, because he gave a guest lecture in one of the Millersville courses. And sadly, we are still seeing remnants of solar cycle 24. So you can't see the date on this, it's so bad. This is a magnetic image. These are magnetic images of the sun, the HMI instrument, showing basically in color where all the, let me go on this side, where all the sunspots essentially are. Like this one, for instance. This one is sunspot 2833, I believe. So it's moving very fast because I've got more than a week worth of data on here. And you can see the new sunspots, and I'll stop in just a moment to show you those new sunspots as they're rotating into view, and talk about the magnetic configuration of that one that's growing so quickly. But here's old region 2833. And it is basically rotating off of the Earth-facing disk. But you can see it had some new emergence, some flux emergence, because you can tell by the different colors that come up. I'm sorry it's moving so quickly. Let's see if I can slow it down just a smidge. There we go. It's jumping frames just because I had so much material. You can actually look at this at higher resolution than what I've got on here, but you can actually see the red regions begin to emerge all around this region. So there is some evolution of this structure. This is why we did get a little bit of flare activity, and as it's moved to the west limb, we've gotten even more flare activity and more solar storm launches from this region. Sadly, of course, it's now going to the sun's far side, so we're not going to get any more from it. But that region has evolved. Now, since I'm already here, I'll wait because these regions are coming in. Here is what was left of that early region, the one that launched that solar storm. And as it comes in, I'll just kind of pause. Well, I'll pause it in a second. There's just nothing here. It's kind of a yellow and green mush. There's just, let me stop for a sec. There's just, look at this. I mean, what? There's just nothing. There's no deep, dark blue or purple. There's no deep, dark red. It's just a plage anymore. It's just remnant stuff. There's nothing here that's going to give us anything. So this is why I say don't worry about this cluster anymore. If I were to look at it in white light, you'd see nothing. It's just boring. So this is what's left. It's just a remnant thing. And this is why I'm looking, hold on. This is why I'm now looking at this region down here. So let's blow up this one. This is the new region. This is, sadly, this is as much as I can blow it up at the moment, at least for a movie. So this is the new region. This is region 2835. Yeah. And right now, it's really not a super complicated region. I'm not seeing anything, but it is emerging quickly. And I can go ahead and I'll play this movie again so you can watch it emerge, and you'll see how quickly it's changing. And so even though it doesn't have a really crazy configuration right now magnetically, I mean, it's you're seeing there's a red polarity which is out, blue polarity goes in, I believe, and then red polarity goes out, blue polarity goes in. You don't like it when they're really super close to each other, but when they're simple, it's not freckled like you have red and blue freckles all over it. That's dangerous when you have red and blue freckles. But when it's simple like this, just a red, blue, red, it's not. Nothing's too crazy about it. But the fact that it's growing quickly, that is what makes it potentially become a flare player. So the region just beneath it, as you can see, once again, not much. I'm not even sure I don't think there's even any signature on the white light of a sunspot here either. But we do have a nice sunspot with this one. So that's why it's been numbered. And if I'll play it from maybe about here. Try to play it slowly. So it'll rotate into view here in a second. Hopefully I didn't make it go too far. Yeah, I did a little bit. I'm looking at the northern regions rotating into view to kind of see, okay, here. So we're getting a little bit of something rotating into view. So watch this region over here. I think it'll be probably up in here somewhere. So let's watch and wait. It did, and I'll show you the sun's far side in just a second. Where are you? There you are. See it? And just look how much it changes. Don't worry about how it's changing. Just look how much it's changing, how big it's getting, how fast. See it changing? See those red regions growing around the blue? See how deep, how fast, how big? So that's why we're watching it, is because it's really emerging. This is a submarine. Remember, I talked about sunspots as submarines. This one is coming up to the surface. It's surfacing very quickly, and that always is giving you a pause to say, okay, this could become a flare player. So that's region 2835, and that's the one we're going to watch right now as far as solar flares are concerned. But I don't think we've seen anything on the sun's front side yet. Now, the one other reason why I wanted to show you this movie of the sun is because of this. Do you see this little thing? Do you see this little thing? See that? We don't want to see this. Here's the equator of the sun right here, okay? This is a low latitude plage. It's not a sunspot, it's not strong enough. But anybody who understands magnetic polarity can tell that this sunspot, this plage, is yellow leading, green trailing, okay? But it's in the northern hemisphere. Even down here, you see these other plages. Notice that they're also yellow leading and green trailing. Get my hand out of the way, okay? So this little guy, this little plage up here in the northern hemisphere has the same polarity as these plages down here in the southern hemisphere. These are solar cycle 25. This is solar cycle, and you can see here, let me get my hand out of the way here. Let me go over here. You can see here, you're supposed to have green leading, yellow trailing in the northern hemisphere right now for solar cycle 25. This has the opposite, and it's low latitude. Anybody who knows has watched my mini courses enough will know that this is a solar cycle 24 plage, meaning solar cycle 24 in the northern hemisphere is still dying. It's not done. We have not passed the terminator yet. Look at this ridiculous thing. Look how long it hangs on. Can you believe this? I am frustrated. I mean, it doesn't last. It does finally disappear. You can see it falling apart. See it getting shredded, right? So now you can hardly tell that it was even there. But it was there, and I saw it, and that was last Thursday. And it's like, as long as we see those sunspots, or those plages with the cycle 24 polarity, we're not past the terminator yet. So this is why solar cycle 25 still hasn't quite kicked on. It's ramping up, but it's going up, down, up, down, up, down. And it's just, it's so frustrating. So I thought I'd just share that little anecdotal thing with you because it's kind of cute. And again, I'm not going to go into detail of that. Just for those of you who are confused, what does the polarity mean? It's called the Hale cycle, and it's something that scientists use to understand how the sun's magnetic field works, because the sun's magnetic field flips every 11 years, and so you can always tell which sunspot or what magnetic submarine is linked to what cycle based on the polarity of that, the colors of that sunspot, that submarine as it pierces the surface of the water, so to speak, in the sun. And so we knew that was a solar cycle 24 sunspot, or plage in this case, because it's not strong enough. Okay, so here's stereo. So is that going to be fast enough? Let's hope. So of course, stereo is staring at the sun from the side. Yeah, let me do this. So I can stand on this side. I like standing on this side. I can see the TV better. So here's the disk, and it's looking very much like the Earth-facing disk because the sun is, stereo is getting close to Earth view now. So we're only seeing a little bit of the side of the sun compared to Earth. But you do notice that these are the regions that are rotating into Earth view. Whoops, let me start it here. These are the regions that are rotating into Earth view now, okay? Both in the north and the south. You'll see very quickly. This is the region that we were hoping was going to give us something, but then it fires off this big solar storm, which you'll see here, boom, right there. I believe that was the big storm that it launched, and it really just hasn't done much since then. It's just kind of died. This is the region that we're seeing. That's just a plage region on the Earth-facing disk. But if you look just past it to this guy right here, I think this is it, you'll see it build. See this thing building? There you go. Look at that thing. Wow. That's region 2835. Okay, so you can see it starts out as basically nothing over here. And just watch how quickly it grows over just like 2 or 3 days. Ready? Especially when it kicks. There you go. Watch this thing grow. Whoosh. Look at that. Wow. It's even, it's not quite launching solar storms, but it is definitely growing. So that's something that we're definitely paying attention to. And stereo, thankfully, is giving us maybe a couple, 2 or 3 days advance notice still, which we're going to lose here in the next year. But the one thing that it also is doing is, see this here? Look, there's a new region. And look at that. Here's some more. Well, I should probably just stop it. When it gets back to that point, I'll stop it. Hold on. So we can chat about it for a sec. Come on. And 8. There, close enough. So here's the things. Here's region 2835 right here. Okay, that's growing really rapidly, and I just showed you the magnetic configuration of that. Just past it, on the other side of that coronal hole, is probably a plage region. I don't know if it's going to be a sunspot, but this looks like it might be. Get my hand in the right place. This guy right here. It also looks like it's growing, not quite as fast as 2835, but this could be region 2836. Either way, in the next week, maybe even less than that, we're going to have this nice view. So our solar flux is going to bump up probably to the mid 80s easily, maybe a little bit higher. We'll see. Meanwhile, we also have, for Aurora people, we do have a coronal hole that's coming, which is nice because this one could give us a little bit of fast solar wind at Earth and might give us a little bit of a solar storm. Probably not huge, but we'll see. But this is awfully nice to be able to see these new regions rotating, or building, growing, and continuing to give us good stuff. EUVI, I like this view. Yeah, it's a great view. For those of you, the reason why EUVI, the green sun, the 195 angstroms is used is because it's a really good kind of like quick look at everything the sun does. You see bright regions really well, you see the corona really well, and you also see coronal holes, right? So that's why the bronze sun that we use with SDO, that's 193 angstroms. This is 195, really close. So they're almost the same view, even though they're two different colors. But yeah, they're really good for quick looks. Okay, so let's see. Any questions on that? Hopefully not. Oh, excellent. I'm so glad you guys are understanding this, and it looks like things are going well. Can you talk about the high cosmic rays we're still getting? I'll talk about it only from the point of view that we're still in the D2 minor range, because I'll show you my 5 days. I'm not going to go into detail on that just because it's not relevant for field day. You know what? And this is the synoptic chart. I don't think I need to really talk about it, other than just to let everybody know that, yes, SWPC did number region 2835. So they're on the ball there. And then let's talk a little bit about the X-ray flux, and I'll talk about the solar flux then shortly thereafter. Let's stand on this side. So here's the X-ray flux. This is our M-flare threat meter. As you can see, M-flares are this line right here. We're nowhere near that. This, as you can see, we actually started, if I get myself out of the view here, you can see we started, this is below the B floor. Sorry if I seem fuzzy. This right here, this line here is the B floor. And so B-class flares are above this line. So we started pretty quiet, and as you can see, we're beginning to ramp up again. So this is showing that by proxy, the solar flux is ramping up, and you'll see that as well when I look at the Penticton data. Had a few flares, but not all that much going on. This was the big monster that was from that region that I was hoping was going to give us something. Instead, it launched this big non-Earth directed solar storm and basically fizzled on us. This flare was probably an M flare. It was probably pretty close. It was like a mid-C flare, even though it wasn't even in view. So that's why I think it was probably an M flare. I don't know how big of an M flare it would have been, but probably would have given us some level of radio blackout. And you know what? I haven't checked for a radiation storm. I probably should do that. But that's why that region fizzled out. That actually did launch that solar storm. Since then, we haven't seen much. And then we got this small little C-class flare today. Whoops, I'm too far. But no, this is not from region, as best I can tell, this is not from region 2835 yet. And someone, if you're in the know and you've seen it, let me know. Correct me if I'm wrong. I don't have an ego about that. Correct me if I'm wrong. But I believe this small C-class flare came from region 2833 as it's rotating to the sun's far side, because it's beginning to pick up steam again. So I don't think we're going to get more activity like this from that region. We're going to have to look for a different kind of activity, maybe flare activity, but probably something more than that from that new region, from the region 2835. So it doesn't mean we're in the clear, but it all depends upon what 2835 does in the next few days. Meanwhile, you can also see, see the bump on in the red? See the bump on stuff? All this stuff kind of growing? That's region 2835. So this extra boost is 2835. Whether or not that solar flux translates to better DXing today, kind of hard to tell. There's always a lag in how the ionosphere responds. So just because we get, even if we jumped up to a solar flux of 100 today, you probably wouldn't necessarily notice it till tomorrow or the next day, because that kind of stuff takes a little while to propagate down into your range and actually ionize things. So there is a lag. Sometimes it's only the speed of gravity waves, but it still takes hours, if not days, for it to happen. So really the solar flux that you're feeling right now is probably the solar flux you're going to see. And that takes me to Penticton solar flux, actual solar flux. So here we go. You probably can't read this very well. Maybe you can. I don't know if you can. This is in solar flux units. So you can see this axis here. It goes from this case, it goes from 60 is the very bottom. 65 is the first tier, first rung. And then it goes up to 115, I believe, 115 up at the very top here. And when you look at at the solar flux back in November, this was that first big tick up that we thought was the terminator. This was the sun faking us out. Remember, solar flux did go up to 115 at that point, or near to, very near 115. So Evelyn, please, leave. Thank you. Come on. I don't know where the battery case is, sweetheart. I don't know. Please. Children. She does that just to get me. I know you're live, Mom, but I'm going to come in and sneak here and heckle you. Oh, goodness. All right. So you can see how rapidly, the reason why I show this is that you can see how rapidly we can rise. And when that terminator hits, we will jump up this quickly. Meanwhile, what we're doing instead, as I flip over to the other side here, what we're doing instead is a slow, ratty climb, right? And I'll zoom in here in a sec. We're doing a slow, ratty climb. We're up now into the 80s. Let me see if I can zoom in to this region here. Okay, so now this scale behind me says 100, 105. So the top horizontal line is 105. Okay, and as you can see over the last few days, each of these is, it's a few days. I probably should zoom in a bit more. Hold on. And I hate the fact that the numbers are so small. You can't read these. So this is each one is 2 days. So if even if you can't read it, it's saying the 23rd of June here. Whoops. This number says 23rd of June. This one says 21st of June. This one says 19th, right? So the very late edge is the 25th, which doesn't look like we've quite recorded a number for that yet. But as you can see, back on like the 22nd of June, we had this massive spike. Okay, anomalous as far as I can tell. I looked at other sources of the data. Most people smooth the data, and this is part of the reason too why they typically only report one solar flux number a day, is that they don't. I mean, you can get ongoing measurements, but the chances of this actually being the real number for that day is probably pretty minimal. And I don't know specifically what happened, but I do believe it was an anomalous reading. So those of you who thought, yay, we're at 105, no, we were not. But we are steadily ramping up, okay? And even if we were at 105 for that day, if it's not sustained, even if this number were real, if it's not sustained, it's not going to affect the ionosphere. So that's the thing, is that flux has to be sustained for it to make a big difference. Right, and even if it were real for whatever reason that we momentarily had that jump up, if it's not sustained, it's not going to help us. So we're sitting here in the low 80s now, and it's going to continue to slowly ramp up like that until we get to that terminator, and then it's going to do what we saw before, which was that incredible jump out. Let's see if I can capture that again. Yeah. That incredible jump. We'll see a jump like this, but then it'll just keep going up, right? And it'll get up to however high it's going to go. But it will jump up quickly. And that's really what we're still waiting for. So hopefully that answers that question. And now I'll go ahead and do a 5-day outlook before we get into the training part, the ionoson part. No, I am standing in the right area. Okay, so for solar storm conditions and aurora possibilities, it's a really quiet week, folks. SWIPSY has high latitude sitting at about unsettled conditions, give or take an unsettled condition. It's pretty much normal to unsettled, but we do have up to about a 20% chance of a minor storm. I honestly think that this is like a catch-all when the wind is just kind of unsettled and a bit turbulent. Because SWIPSY also gives about a 20% chance of active conditions as well. I would imagine it's closer to active conditions than minor storm conditions, but I always report the higher number just in case to encapsulate it. And the higher number that is the most probable. And so since they're saying both 20% chance of active and 20% of minor, I threw in the 20% of minor chance in these regions in both the Saturday and oh, cute, Saturday and Thursday. Don't you love it? Saturday, I didn't correct the dates. That is so cute. Let me do that right now so that it's not permanently set like that. That's horrible. Look at me. This is what happens when I try to do things fast, right? I need people to keep me honest here. Sunday, Monday, Tuesday, so I don't freak out. I changed the dates and then completely spaced on changing the days. Anybody want your week to go back and not have a weekend? What? Unable to load. Okay, it just, what did you do to me? Saturday, Sunday, Monday, Tuesday. Okay. So you guys get to see me do this in real time. Isn't that cute? Probably not. It's informal, guys. This is normally what my Patreon group gets to see, my Patreon community gets to see. They get to see how the sausage is made. So you guys get to watch that in real time. Okay, so now that I don't confuse you, let's try this. Let's try it again. There we go. That looks better. Okay, so what I did is I went ahead and I used, because there is a small coronal hole that is rotating. It's going to go into the Earth strike zone in the next couple days. It's really teeny tiny, and I'm not expecting much. But just in case, I went ahead and gave the space, the SWIPSI prediction at their highest level for these 2 days. Because if it's going to hit us, it's going to be in this region. So high latitudes, yeah, you may get a little something. I wouldn't count on it, but you may get a little something. As far as mid latitudes go, we've got a quiet week. I mean, it's going to be nice, just perfect for field day, just really kind of just steady and slow, and it'll just be really uneventful. And then regarding solar flare and particle radiation storms, we don't have any chance for M-class flares, at least not yet, although we are watching region 2835. Now, region 2833 is going to disappear off the Earth-facing disk here in the next day or so. And so that's why you see that sunspot number drop off here. The Space Weather Prediction Center has the solar flux sitting at about 82. I think right now it's 81, or at least as of noon yesterday, it was 81. They've forecasted it to be 82. I actually put 83 and then up, because I do think it's going to climb with these new regions rotating into view. 2833 just isn't adding all that much to the mix at this point. So I really do believe that we'll start climbing up. Whether we get beyond 85 and a little bit higher, I don't know, but there is a chance, especially with these the two new regions that we're seeing on Stereo's far side. But that won't happen. If we get there, that won't happen until the beginning of next week, so after field day. And then here's what the whole thing with the cosmic rays. We're still, like I said, we're still seeing remnants of solar cycle 24. So until that flip switches, or that switch flip that flips, however you want to say it, we're still sitting at the D2 minor range for radiation. And that's because of the cosmic ray flux is coming in a lot more intensely than we'd like. So, and the D2 minor range is for people who are flying above 11,000 kilometers, or, basically 39,000 feet. And especially important for people who fly at high latitudes and high altitudes, and fly for long periods of time, right? And this does, of course, include the prenatal passengers. So pregnant women, keep this in mind. These low solar cycles just give us a lot of cosmic ray flux. So we just have to deal with that for a few more, maybe months, before things go back into the D1 range, which will be nominal. And I'll be happy for that. Okay, so let me pause here before I get into some fun stuff, which is looking at MUF data. As a matter of fact, I'll put an MUF plot up here in a sec. So this is one of the plots that's dead right now. Where's my MUF? Okay, here's MUF. So I'll put this up behind me, and we'll start talking about this in a second. Any questions on where we are right now? And for those of you who just wanted the forecast, feel free to drop off, right? This is going to go into a little bit of a tutorial specifically for people on field day and my Patreon followers who have asked me specifically about MUF and how do you get there and what do you do and blah, blah, blah. Okay, so feel free, don't feel like you have to linger if you're ready to drop off. So, and obviously any questions before I continue. Paul says, can you explain why we are seeing cosmic ray maximum from solar cycle 24? Cosmic rays always peak when the sun is its weakest. So at solar minimum is when cosmic ray flux is always the most intense. And the reason for that is because of the magnetic shield that the sun has, right? The sun, just like Earth, has its own magnetic shield. In fact, that shield is what we call the heliosphere, and it protects the entire solar system. Okay, it shields us out from all the other junk from all the other stars in the Milky Way that we're sitting in. And there's a lot of, space is not a habitable place in general. Earth lulls us into a sense of complacency that space is far more benign than it is. Space is honestly, it's radioactive. There's a lot of stuff going on out there, and very energetic particles that can really hurt people if they're not protected. And luckily, our star, with its own magnetic field, shields out a lot of that stuff. But the problem is that the star, it has its cycles, right? So sometimes that shield is really strong and sometimes that shield is really weak. And so when that shield is really strong, the cosmic ray flux goes down because the sun is shielding out that stuff from even getting into our solar system. But when we go to solar minimum, that shield weakens, and because it's the magnetic field strength that is falling. And so as that weakens, then the cosmic ray flux can come in a bit more. And it's every other cycle that the cosmic ray flux really comes in. So as a matter of fact, this last solar cycle, the cosmic ray flux actually didn't come in as much as it will at the minimum of the cycle upcoming. So in another, 8-9 years, we'll start seeing that cosmic ray flux really begin to creep up again. And it'll creep up possibly even higher than it has in this cycle, depending upon, during this solar minimum, depending upon what this cycle does. So that's really what it is. It's anti-correlated, and that's good and bad. It's good in the sense that we don't have to deal with solar storms and solar radiation storms at the same time we have to deal with big cosmic ray flux. So it's not one on top of the other, thank goodness. That helps us in terms of space travel and keeping our satellites safe and people on airplanes, right? But the problem is it also means that there is no such time as safe, as clean and quiet space weather, because when our sun is active, we have to deal with radiation storms from the sun. So it's kind of like cosmic rays from the sun, right? Our own star gives us radiation storms. But then when our star quiets down, then it stops sending radiation storms, but then it lets radiation storms from the universe, the rest of the galactic sphere, enter our solar system. So we get bathed in a cosmic ray bath that are essentially radiation storms. So do you want the radiation storm from our star, or do you want it from other stars? It's really just a give and take, one or the other. You're going to get it. So that's the good and the bad about space weather. But yeah, that's how it works with when it comes to radiation storms. Okay, any other questions on that? Says, thanks to Tamitha Now Terminator. What's your thoughts? Will this end up being a more active cycle or less active? Conflicting science. Well, that is the name of the game, right? A lot of people think that it's only fringe science that conflicts. No, mainstream players, we argue all the time. I mean, that's how science progresses. So if we didn't have conflicting science, then you'd think the field were dead. That tells you how little we know about our sun, to have scientists who have studied it their whole lives still not agree. And honestly, the way this cycle is coming, is unfolding. It looks like we're at least going to see the mean. So if you take all the solar cycles, all 24 of them prior to this cycle, and you average them, their ups and downs, and how long are they, and how tall are they? If you just do that over all the 24 prior cycles and say that's the prediction for this upcoming cycle, that prediction actually looks like it's going to be pretty good for this particular cycle. And so, do I think it's going to be a massive cycle like Scott is hoping? I'm not as confident as he is in that side of the work, just because I'm trying to be a little bit more conservative in that sense, right? And I'm hoping that it's a big cycle, but I'm not as confident. What I'm pretty confident in is that it is going to pick up faster than the consensus. I don't think that the consensus is going to be, because they're saying that it's not even going to pick up for another year or more, and I think they're going to be wrong in that regard. The way the solar flux is ramping up, it really looks like it's closer to the Macintosh at least cycle growth, the growth curve, how quickly it's going to ramp up. Where it ultimately will be in terms of amplitude, how many sunspots, how big is it going to be? Is it going to be as big as his earlier prediction, that it's going to be as big as cycle 19? Likely not. And I think even he agrees with that, because it's taken too long to ramp up. If that November, back in November 2020, that false start, if that had been the real thing, I would have said yes. I would have said, "Oh my goodness, Scott, you guys are, your team is on the money." And I really thought at that time that was going to happen. So the fact that it's kind of faked us out, it was like, oh, what happened there? But it's still nonetheless ramping up faster than the consensus prediction. So that's to many of us, that's great news, because I would prefer to have a more active cycle than a less active cycle, because that means likely less Carrington class events. I would much rather have more extreme events that we can handle than 1 or 2 whoppers that we can't. Okay, and it's the lower cycles that are actually, from that perspective, more dangerous. So I would rather side on the side of more activity and less, devastating solar storms than less activity and then the chance of playing Russian roulette with a really big one. Right? There were 2, if not 3, Carrington class CMEs, big coronal mass ejections events that occurred last cycle. You guys have probably heard about one. Maybe you've heard about 2 of them, but I know you've heard about one. That's the 2012. But there were actually 2 of them in 2017. And we got clipped by one. Neither of them hit us head on. So anyway, enough of that. Hopefully that answered that question. Okay, so I will, yay, I made it for your live. You're very welcome. Boom, yes. Okay, I'll answer one more question, because that's Bart. Hi, Bart. Tamitha, how long must a high solar flux be sustained for it to affect the ionosphere? Well, the thing is, you can get transient effects and then things will calm back down. But we do have, the issue is obviously which layer are we talking about? And obviously it's a function of, I hate to say this, but it's also a function of what terrestrial weather is doing. A lot of things in the upper atmosphere have to propagate through what we call gravity waves, vertical gravity waves that go up and down. And even terrestrial weather has to propagate up into the ionosphere using waves. And then there's got to be all this mixing. So you can get radiation that goes to the highest layers in the upper atmosphere, but then those layers then have to kind of, I don't want to say homogenize, but there's all these different processes that then try to distribute that charge, that free charge. And there's a lot of atmospheric chemistry that goes on, and a lot of this happens with, believe it or not, the metallic ions that are in the upper atmosphere, as I'm learning, because I'm beginning to learn all this stuff now. So the atmospheric chemistry really hinges a lot on different types of metallic ions that have all these free electrons. And a lot of that, people say, why is there metal in the upper atmosphere? Meteors. We have lots of meteor dust all over the place, and so there's sodium ions. There's just all sorts of different types, and it's very interesting as I read all this stuff how vertical wind shear and gravity waves really affect the layers, and how they affect how disturbances propagate both up and down into the ionosphere and out of the ionosphere. So it takes hours at least. And in terms of sustaining things, it can take hours to cause something to have an effect that you might notice, and then it takes hours for that to drain away. So something is constantly draining away because there's all these recombination processes that occur. So the time scale is typically about hours before you recognize something, and sometimes days. And if something is happening on that time scale, it's changing that quickly, like over the course of a day, you're not even going to really notice it. But if it's sustained over multiple days or sustained over a week, then you will start noticing it. Give it about, half a day or so. But remember, as the Earth rotates, right, you're not always shining, that solar flux is not always hitting the same part of the atmosphere. So it's not like a light bulb on a hot rock or something that's just constantly shining. As the Earth rotates around, a different part of that ionosphere is being being shined upon, so to speak. So it's being ionized. And so you kind of have to realize that you've got these processes that are happening on our time scales, moving up and down with the mixing in the atmosphere. But then you've got something that works on the time scale of a full day, right? Because if you're shining down on the ionosphere here at high noon, well, that then rotates into the afternoon and then rotates to the night side and then has to rotate back to the day side again. And it's not getting that same constant solar flux. It's not getting that same constant irradiation and ionization all the time because of that rotation of the Earth. So you've got competing time scales. And that's part of the reason why as the solar flux ramps up, you don't see that instantaneous change, right? You see it delayed, sometimes on time scales of a few hours, sometimes on time scales of days. And that's really because it's just this process. Hopefully that clarifies it a little bit, or at least gives you an appreciation for why it takes, why it's not instantaneous. Okay, hopefully that helps. And I need to learn a lot more about ionospheric physics. So, Tesla, meteor dust must be hard on Tesla's paint job. Yeah, I would think it's not even the meteor dust on especially on that Tesla near Mars. It's the radiation, the particle radiation, the solar radiation storms. That's probably the most intense. All right, so what I'm going to do now is I'm going to talk a little bit about, for those of you who want to know about MUF, there are a lot of different places you can go to get MUF plots. Here's one. It's not necessarily my favorite. My favorite is actually one from Giro that I'll show you examples of. But right now their site is down. So yes, I will show you links to this stuff, but I want to just kind of show this one right away. I wonder if I can make it just a little bit larger. This is one from prop.kc2g.com. This is actually linked in NOAA's website, so you can get access to that. And again, like I said, I'll show it to you in a minute, but you can see it's the full globe, okay, and this is a contour plot, right? So MUF, of course, is the maximum usable frequency. And we'll talk a little bit more about what MUF is in a minute. But down here, just for those who already know and know how to use the data if they're given it, here is the scale, okay? So as you can see, this scale goes from really low frequencies, down below 2 and 3. You can see 5.3, 7, 10.1 up 14, up past 30. So we're easily talking about the HF range, right? The entire HF range. And if you look here, so the dark colors, the purples, are the low frequencies, and the yellows are the higher frequencies to be used. And it's a contour plot. You can also see the terminator, right? You can see where the shade is, and it makes sense, right? At nighttime, you are going to be using lower frequencies. The total electron content in the upper ionosphere is lower, so that brings you down. The higher the electron content you have, the higher frequencies you can use. You might notice on the day side, so when we get to the day side, you're going to see overall things that move more into the green and to the yellow, okay, both at mid-latitudes and especially at low latitudes. You might notice, in fact, the two bands. See this band here and this band here. These are the equatorial anomalies, or well, it is the equatorial anomaly. This is a day-side phenomenon. It has to do with the fountain effect. It has to do with Earth's magnetic shield and how particles move, especially electrons move in the Earth's magnetic field just at low latitudes. You actually have a drift that pulls these particles up, and then they do a fountain. They kind of go up, and then they spiral around the magnetic field and actually come back down and rain back down on Earth. Right at the magnetic equator, that's right where the middle of it is. That's where they go up, they rise, and then they spiral off around the magnetic field and follow it down on either side. And so you get this, splashing back to Earth here at the one side of the equator and here on the other side of the equator. So it's kind of a neat thing where they go up at the equator and then they splash back down on either side. And that creates both bands. Typically that band is stronger in the afternoon. As you can see, it's stronger in the afternoon sector than it is in the morning sector. This is the morning. And yes, that does mean you have a higher maximum usable frequency in the yellow regions. okay, where there's higher total electron content, because that's where the electrons are concentrated as they spiral and fall back down. Sadly, though, you'd think that that's wonderful. It's actually not, because a lot of times it causes a barrier. Anybody who's in this equatorial region and the low latitude regions oftentimes can't transmit out or can't receive beyond this. They're stuck with whatever's in this region. And so they get isolated on the day side. It's really frustrating for them. Of course, it releases at night because there's not anything like that at night, but you have to use different frequencies. So if you are a dayside person and you are contacting people during field day, doing a lot of really good DXing, you might notice you're having a little bit of difficulty getting to, let's say, Brazil. This is also why Brazil's GPS is wonky a lot of the time, especially in the summer, their summer. But this equatorial anomaly is an issue. So if you ever want to get to those regions and you're having issues during the day, try doing it at night on different frequencies if you have the capability, okay? Because that equatorial anomaly is not an issue. So that is an overview of this map. And here is I think I have it on, come on. Oh, there you go. You gave me for a sec. Thank you. I don't know why. Why is it letting me do it sometimes and not others? I don't want to make it, well, if I make it super huge, it won't be easy. Okay. That one is this link right here. And I guess I could put this in the description for you guys. This is one that is working right now. Now, one thing I haven't talked about yet is the 3,000, see it says 3,000 kilometers? Right. That map is, and most of them are, they are geared toward the maximum usable frequency for a contact between the transmitter and the receiver of 3,000 kilometers. Believe it or not, MUF it's kind of a squishy parameter because it really depends upon how far you want to DX, how far you want to get your contact, how if you want to talk really close, very closely to someone, the MUF is going to be different than someone who's much further away. As a matter of fact, MUF goes up for distances that are further, and we'll talk about that in a minute. But here is that particular plot. There's also one at hfpropagation.com. I'll show you that here in a second. So you've got those two links. And then I'll also go into the NOAA Ionosonde Digisonde link. And let me get out of the way there. So anybody who wants to write that down. I'm sorry I didn't have time to put it in the description as of yet, but I will. And there's a link here. And this link has lots of good stuff for you. Lots of pictures, lots of data. They even plot FOF2 just over the course of days so that you can kind of see what FOF2 is, and we'll talk about that in a second. Sadly, these are not my favorites. My favorites are these up here, and I gave you the links to those as well. The problem is those are down right now. Oh, it's so frustrating. These I love the Giro, the UML stuff, and I love PropQuest. PropQuest, if you don't know Jim Bacon's work, you really should, and I forget his call sign, but if you don't know Jim Bacon's work, really go to PropQuest. It's fantastic. But sadly, I think there's a good chance that his FOF2 and MUF plots are based on the Giro stuff, and that's why they're both down right now. So what timing, right? Right at field day, very frustrating. But at any rate, those are my favorites, and I'll show you some archive stuff, and I'll show you why they're my favorites in a second. But to go back to, let's see, do I go back this way? Yeah. So that is the propkc2g.com. And then what do I want to show here? Here's the other one. Here's the hfpropagation.com. These are nice because they go by location, right? So you've got a global one here, but then if you want to zoom in on certain locations, you can do the same. They've got their color bars, right? And these, I do believe, are MUF. They're not FOF2. Or megahertz 3 to 21. Yeah. It can be that high. They're definitely going to be MUF. So you can see their color bar up here, and they do, as you can see, they do refresh. And you can get these at QRZ, I believe. But if you haven't gone to hfpropagation.com, that's the place to go, or that's another place to go. And yes, you can see they're all over. Okay. So those of you who understand how to read contour plots. It's really the same kind of thing. They're all color coded, and they're all color coded by region. It'll give you a nice head start. And I'll put all of these links in the description for you. Yeah, hfpropagation.com. So I've got that. Okay, just checking. Now, here, whoops, I don't want to go to that yet. Where is the space? Okay, there we go. So this is the NOAA link that I showed you, that I talked about. And the nice thing about the NOAA link is that you can get data. The reason why I don't typically use this link is because the plots are not very pretty. This is why I like Geo, and I'll show you an example of Geo stuff in a minute. But you can get lots of data from them. You can get real-time ionograms from all the stations, but some of them are really nasty looking. This MUF map and the 3,000 is that 3,000 kilometer hop again. That is the map I just showed you, the big one, that big global map that was very, very pretty at not Prop UK. This one. Here, I'll just click to it. See, this one. So the Prop KC2G. Okay. So you've got that there, and then you can also get other things like the real-time FOF2, like I talked about, for all sorts of different places. And this is, I'm going to do Boulder just to look at that Digisonde. Totally different type of plot. It's not an ionosonde plot. This is just simply plotting FOF2 for those of you who know what it is already. Over the course of days, you can actually see over each day at local time, these are local times, you can get an idea what the FOF2 is essentially for that boulder, or for that particular ionosonde. This is the Boulder ionosonde. And a rule of thumb for a 3,000 kilometer hop, it's a rule of thumb, it's not perfect, but if you want MUF from this, essentially multiply by 4, multiply FOF2 by 4, okay? It overestimates the high stuff. I think it underestimates the low stuff, but it's, as a rule of thumb, for those of you who just kind of want a quick and dirty back of the envelope calculation, you can use FOF2s, and here's obviously some spread in them, but you can use FOF2 to get you your MUF by using that little trick. And I'm sure ionospheric physicists will groan when they hear me say that, but sorry guys, if we're just doing a quick and dirty and everybody's working stations and they just want to take a look at a map and kind of get an idea, and they've got an ionosonde or something there and they don't have a good calculation of MUF, that is kind of a back of the envelope calculation. And there are tons of them, as you can see. Okay. The sad thing is that some of these pictures are awful. I'm not going to go into this. I'm going to talk about, let's see. I was going to show, what was I going to show? I was going to show, I'll show that in a second. Oh, let me show a real ionogram. Okay, so here's some ionograms. We're going to start getting into we're going to start getting into ionosondes and ionograms and talk about them in earnest. Sadly, some of these are really, some of them don't work. Like that one doesn't have good data. There's one that doesn't have anything at all. This is why I don't like this site. Here's an ionosonde data ionogram. I'm not going to talk about this one yet because we're going to I'm going to teach a little bit about ionograms and how to read them. This is one that looks reasonably good. There are some that look absolutely horrible, but you will see up in the top, you'll see FOF2, you'll see FOF1. Those are the frequencies using NVIS, using near vertical incident skywave. Where they're sounding basically what is the highest frequency they can use to penetrate that range. Now that's not the same thing as MUF, because these are going straight up and then straight back down, where most people who are doing DX, you don't want to talk to yourself, right? You're not going to go straight up and then straight back down again. You want to talk to somebody over there. So your signal is not going to be going straight up at essentially zenith. You're going to be pointing at some off angle. And we'll talk about more about how that affects the frequencies that you use and why that's so different than this. But you can see they even have, in some of these, they do have MUF calculated. Again, the MUF is calculated at 3,000. So they see MUF and then they've got a D in the parenthesis. See that D in parentheses? See the D down here? It says 3,000. That's for a 3,000 kilometer hop. Okay. So all of them, that's a pretty standard thing. So if you're planning on doing a communication with somebody who's closer to you than that, you're going to have to drop your frequency a little bit. This MUF is going to be overestimating the maximum usable frequency. Okay. I'll talk about it in a sec, just a second. This is just for people who might know what they're looking for. So you can use this site to get lots of different ionosons all over the world. Yuck. Some of them, like I said, look terrible. This is not my favorite site. My favorite site is way different than this. But it is very useful for lots of stuff, okay? So you can get FOF2, you can get FOF1, you can get the height of the ionosphere, that's the HM level. You can get SE level FOE products. So for the E layer, you can get the same kind of idea from the E layer. I prefer Prop UK for that, for Jim Bacon stuff, but sadly, it's not, it's not working right now. That was very frustrating for me. And here is, just to give you an idea, here is a plot of where a lot of the ionosons in these data networks are. They're not everywhere, okay? So there is going to be, even just looking at the United States, right? There's going to be holes, right? And there's going to be stuff where local propagation conditions are different than what the ionosons say they are. And all those maps are going to be smeared out to some degree, right? They're just smoothing this stuff. And so local perturbations due to weather, as we all know, weather happens on scales that are even smaller than this. So you're not going to get, perfect data, perfect modeling from any of these ionosons, but you want to choose one that's as close to you or as close, or maybe even look at ones that are just next to you and then possibly ones that are next to them. Whoever it is you're trying to contact or wherever you're trying to DX, to be able to get an idea of what the conditions are between you and them. So, the nice thing is it gives you, when you look at real ionoson data, it gives you a much faster update and a much clearer picture. And if you're just in a small region, then you can just look at one ionoson and probably get a better feel for it. All right, what am I going to do next? Am I ready to talk about? You know what I'll do next, I'm going to get to this bit here in a second. I like I like the plots on this one. So this is what I'm going to use to kind of talk a little bit more about what MUF is and all that other good stuff. But before I do that, do I have it here? I want to show you what my favorite site looks like that I wasn't able to show. Where is my PowerPoint? Yeah. This is why I'm so upset. Look how cool this is. Guys, my favorite site is down. Here's my favorite site. Okay, it's giro.uml.edu. And what Giro does is that they create, and you can see the ionoson networks. Here is, in this case, they're showing, this is, believe this is this MUF or FO? No, this is FOF2. So this is an FOF2 animation. Like I said, you can get MUF from FOF2. We'll talk more about it in a second. But here's the animation for FOF2. As you can see, the frequencies are slightly lower than what you would expect for an MUF. This is for near vertical incidence, so essentially up and down, which is the lowest frequency. And we'll talk about why in a second. But it's essentially the lowest frequency you can use. And then you can also get HM. Why aren't you? Okay, there you go. You can also get HM-F2 animations, which are showing you where the height of that layer of the in this case, the F2 layer is. So it's the maximum height. So height maximum, HM, F2. You can also get HM, F1 if you're looking for, the F1 layer. You can also get HME, right, if you're looking for the height of the E layer. And so it's plotting that, and you can see there's a scale showing in kilometers how high that layer is. So I love the Giro site because it gives this stuff, and it doesn't just give a picture. It actually takes the ionosons and digisons, and it creates these wonderful animated views of the past 24 hours or something like that, with a little nice little time thing if it will continue. I don't know why it keeps hanging up, but I think it'll start again in a second. But you can also see the magnetic equator. They actually draw, that's this horizontal line that has this little bloop in it right here near South America. And you can see in the day side, why is it taking so long to restart? There we go. I don't know why it does that. you can actually see where the day side is. You can see that equatorial anomaly. See how it's following the day side? So you can actually see there's a little area of the terminator, and you can see where the day side is because it's showing, you know, the higher FOF2, which also would be a higher MUF as well. So it's nice to see that. What also the GIRO site shows, if you dig into the ionogram movies, is that on this site here, when it's working, you will load in a checkerboard fashion, all the way across the screen, all the way down, movies like this. And they're all different ionosons, and they all are showing movement over time. And it is just such a nice way of showing the evolution from the day to the night, how the ionosons change. And it's a nice, very rapid, quick look at ionoson data. So keep this link, even though it's not working right now, keep this link in your, in your back pocket if you want to know, if you want to look at ionograms and digisons, dynosons, for really good information about in your locale, because they have a massive list, and like I said, they take time to animate this stuff. And I'm trying to think, is there anything else I wanted to say about this site? I don't think so. Sorry, this was a talk I gave, so I'm trying to see if there's any other information on this talk. I just wish I could have done this live for you. Actually, I will use it for this. So I will talk a little bit about dynosons and ionosons and how to read the data. And I'm trying to think, do I want to talk about that first or this first? I've never taught this stuff in this fashion, so I'm just trying to think what in my mind, what would be easier for you to digest. Let me do this first, because this just talks about the waves, that how radio propagation works. Okay, so before I get into ionosons and digisons, let me just kind of first give you a feel for the principle, a little bit of the principles. I'm not going to go into it in super depth. I will do that. I will go into more depth when I do a mini course. But this is, remember, just on the tail end of a forecast. So when we're talking about ionosons and digisons, we're really talking about something that is doing a weird type of propagation, right? It's literally going up and then back down. So if you look at this as kind of like a V, you're looking at a V that's almost collapsed on itself. It's an inverted V. This is transmission, and then it goes up to a skywave. It comes up to a layer, bounces off that layer, and comes back down, right? That's an inverted V, right? Well, if you squish that V and make it super, super narrow, you do this, right? It becomes like what? Just a very thin V. And that's kind of what an ionoson and digison does. It literally sends a signal straight up, and then that signal is reflected back down if the frequency is within the right range. It's not too high. This is what an ionoson or digisond often looks like. You've got a transmitting antenna and then a receiving antenna right next to each other. Okay, so it just goes straight up and straight back down. Now, here's how to understand, and so this is how to understand the propagation from a layman's perspective. And of course, again, ionospheric physicists, if you are in there in the audience, please do your eye rolling quietly, because there's going to be so much I'm going to gloss over. But this is just to help for field day. So we're thinking about this from this perspective, that we're just piercing, like trying to pierce through the layers, okay? And how you do that is that you basically sound the layers. You find out how thick that layer is, how well formed it is, by changing the frequency of the transmission that you're sending, right? The higher frequency you go, eventually you'll be able to pierce through that layer, because the layer isn't thick enough. It doesn't have the right stuft, so to speak, density to be able to keep up with the frequency of the transmission. The frequency of the transmission is so fast that the electrons in that layer, there's not enough of them, and they're not dense enough to be able to respond at that frequency. It just so the frequency just goes through, and the electrons go, wait, did you hear something? Right? But if you're lower than that frequency, the electrons can respond, and they can move and shake, and they actually will, like in a sense, mimic your radio signal and radio it back down to you. In this case, you're doing it straight up and straight down, which is really like a needle. You're trying to poke through that ionosphere. That's exactly what these things are doing. And the analogy that I find the easiest, and the mechanics are totally different, but the analogy that's easiest to understand in terms of why you would do it this way as opposed to just a normal radio propagation, DXing, contesting, trying to contact people, is that it's kind of like skipping a stone on a water, right? Have you ever take a flat stone and skip, play skipping? It's the same kind of thing. If you try to skip a stone by dropping it straight into the water, well, obviously it's going to pierce right through that water very, very quickly. You can't skip a stone that way at all, right? How you skip a stone and have more skips and get it to go further is you try to throw it alongside the water, right? As parallel to the water's edge as you can get, right? To that layer as you can get. And that's the point, is if you can skip that stone, if you can get your stone to ride on top of that water, it's going to bounce off that water and then bounce again and bounce again and bounce again, right? Depending upon how angled you are hitting the surface of that water, well, it may only bounce a couple times before it completely dives in. But if you get it really close to the edge of that water, man, you can watch that thing go right, and skip all the way down and go really long distance, right? That's the point. It's exactly the same kind of point when we talk about the ionosphere and doing DX. And of course, what do they call it? Skip, right? If you are piercing the water, dropping the stone in the water, I mean, now we have to go up instead of down, but if you're dropping the stone in the water up, just like this, it's going to pierce very quickly, as almost, it doesn't take much to pierce that layer, right? Pierce the layer of the water if you're skipping a stone, or pierce the ionosphere with the stone that is your radio transmission, if you're going to drop it straight up, right, straight through that layer. But if you're DXing, that's not what you're going to do. You're going to want to try to bounce it by skipping it, right? You're going to want to try to get closer to be parallel to that layer, right? And the more parallel you can get to that layer, in other words, the more that incident angle, well, I want to say the incident angle, let's talk about the transmission angle. The more that transmission angle here can be closer to where the parallel to that layer. So if you're trying to get to the F layer, the more that transmission angle gets lower and lower, gets smaller and smaller, so that your radio signal actually parallels that layer. It's just like that skipping stone where you're just skipping across the edge of that water. In this case, the edge of that water is the underside of the F layer. That's what we're talking about, to be consistent with this diagram. Okay, so you want that to be that transmission angle to be low, right? The sad thing, of course, is that if you get it super low, well, it's going to take you how many miles before you finally get up to that layer, because you have to draw that vector way out. And of course, if you go straight up into the ionosphere, then you don't have to go very far at all. You can just go straight up there. But you're going to pierce it very, very quickly with a very low frequency. If you skip that stone by getting closer to the parallel to where that layer is, you can actually go into higher frequencies. So the lower that transmission angle is, right, the more parallel your radio signal is to that layer, the better chance it has of skipping, the less energy it takes, the less problem the ionosphere has reflecting that signal back to you. The less problem that ionosphere has, that water has, of skipping that stone, right, that would normally pierce right through it. Okay, so you can use higher and higher frequencies the lower that transmission angle is. You're skipping that stone further and further and further. Of course, the problem is power, right? How many people have a 5,000 watt station, right? You can't, there's only a limited amount of power. You can only throw that stone so hard before, it just kind of punkers out. And it's the same thing with radio signals, right? So you have to kind of play this game between how your transmission angle, right, or how far you want that transmission to go, and frequency and power. Okay, so when you see MUF, right, they're taking something that had a transmission angle of essentially 90 degrees, right, straight up. That is your FOF2. That is basically the lowest frequency that you could use. If you were going straight up, I mean, this is the maximum usable frequency if you're going straight up. But just like dropping a stone in the water, that's not very good. You're not going to skip very well. But if you make that transmission angle tilt, then your frequency, your maximum usable frequency, will go up. And it goes up based on that transmission angle, okay? Now, it's like skipping a stone higher. So when they make these plots that say MUF as a function of D meaning distance, they say, well, obviously your MUF will change depending upon how your V, how far do you want that signal to go, right? If you want your inverted V, instead of being straight up and down, now you want it slightly out, maybe 100 kilometers, 200 kilometers, 500 kilometers, 3,000 kilometers. I mean, how far do you want your V to be spread, right? This, when it comes to bouncing off the ionosphere, right, is a function of transmission angle. See, because they've defined it here, right? Your angle from the ground, right? So your real super tight V's are like this, less tight V's or less, lower V's are like this, lower V's are still. Your MUF is going to go up as your V spreads, right? So this will have, let's say the first one that actually folds into a V, this one will have a smaller MUF, this one will have a bigger MUF, and this one down here will have even a bigger MUF. So they have to standardize it. So when you see that as a function, MUF, and they say like parentheses D, and then they say D equals 3,000, well, they're talking about the MUF for a signal, let's say, that has, let's do this middle one. Let's say this here, well, they're not actually showing it because they've actually got it. The range is kilometers. The MUF would be here is your transmitter, and you do something where, let's see if I can draw it. It's going to be hard on the green screen. You have a V that comes up right about in the middle and then bounces back down to 3,000 kilometers. Okay, that's how they make those charts. So they're telling you, okay, we'll give you MUF in a plot, but we're going to assume you want a DX 3,000 kilometers. If you want a DX less than that, well, your MUF is going to have to go down because your V isn't so flat. Your V is going to have to come in a little bit, right? Your transmission angle, this angle, is going to go up a little bit, which means the stone that you're skipping on the water, you're not going to be quite as flat to that water. You're actually going to be up a little bit. So this is why MUF is squishy. Okay, MUF is also squishy because the other thing that matters is the incident angle. This is the angle. If here is the layer, the incident angle is the angle basically straight perpendicular from that layer, right? And you have your transmission has to make an angle there with the layer. The problem is layers do this. In real life, layers aren't flat. Layers do this. So what do you think that incident angle is doing? It's being defined all the time. So MUF is always going to warble a little bit and going to be off of what a ionosonde is going to say it should be when you do your calculations, because the layer location and the layer angle here at this ionosonde may not be what it is over here. That layer is not going to be this smooth little thing. It's going to be doing, with all sorts of weird perturbations. This is why radio propagation can get weird in and around big, massive storms, storm cells and hurricanes and things like that, because there's a lot of stuff that gets propagated up, usually through gravity waves, up to the ionosphere, and the layers are just going, whoa, because they're on this waterbed of a neutral atmosphere, just kind of wiggling and shifting. So that's part of the reason why radio transmission and radio propagation is so hard to deal with, and why people do NVIS. They do vertical skywave stuff, because it's a lot easier to know how heavy of a stone do I need to break through the surface of the water to get it to sink, right? It's a lot easier to be able to do that and know the absolute hardest way to skip a stone. because it gives them a real localized understanding of what they do. It's also the most robust kind of radio propagation you can do, is to have that usable frequency be super low. Sadly, that's also some of the most, it's painful with space weather. So hopefully that helps a little bit in understanding why, first of all, what MUF is, why it differs from FOF2. Because you're changing that V. You're not going a straight vertical V, you're spreading out that V. And the more you can, just like skipping a stone, the more parallel to that, to that layer you can get, the bigger chance you have of skipping that stone with a higher frequency than having it pierce through that ionosphere. And I hope that helps. I have no idea if that was clear or terrible. So, what is this about? This is for field day. So this is very specific stuff that we're talking about now. The forecast was earlier. This is just for mainly my Patreon users. So let me quickly then go back, if I can get my PowerPoint up. For those of you who want to know about ionosonts, here is a very quick and dirty way of looking at, way of understanding an ionosont. Okay, so here's one. This was at Wallops Island. This is for a talk I gave a little while ago, and you can see lots of stuff going on here. Down at the bottom, you're looking at frequency, okay, from 1 to, in this case, about 18 megahertz. And up here in the vertical, you're looking at height, virtual range, okay. Now remember, ionosons and digisons go straight up. They're dropping that stone in the water. They want to know what is the frequency at which it pierces. That stone actually will not sit on top of that water and be reflected back to me. It'll actually be pierced through the water. And of course, that's done with frequency. Now, you'll notice, first thing you'll notice that there's 1, 2, 3. Whoops, I did it wrong. Sorry, let me point better. There's essentially 1, 2 sets, 3 sets of traces. Okay. The traces that you always want to pay attention to are the ones that are the lowest at that particular frequency. So if you see any ones that overlap each other at the same frequency, right, like this does, nothing overlaps, but as soon as you get to about here, you start seeing not just this trace, this set of traces here, but you see one on top of it. Okay, this trace up here. Always look at the lowest one. And the reason for that is because what ends up happening is that you'll get a signal that goes up to the ionosphere like a dribbling basketball. It goes up to the ionosphere, comes back down, hits the ground, goes back up to the ionosphere, comes back down, and it attenuates, slowly attenuates. And so what you're seeing here is a second hop. You're actually seeing an echo, in a sense, of what has been recorded here. Okay. So breaking it down in a nutshell, this is just an idealized version of it. You're seeing, again, frequency on the bottom, and you're seeing height on the top, or range, on the vertical, okay? The first one that you're going to see as this ionoson sweeps through frequencies, so it goes from low frequency to high frequency. Think of it going whoop, whoop, okay? Not in sound, obviously, but it's doing that in frequency. So as it starts in low frequency, it will first sound, it'll get through the D layer, and it'll first start sounding the height of that E layer. Okay, that's going to be the first thing you typically see. Okay, so it's finding the height of that E layer, and then as it begins to get to the point where that E layer can no longer, it's beginning to pierce through that E layer because the density of that E layer isn't strong enough. It's going up to a high enough frequency that it begins to pierce that E layer. Where, that's where you start seeing it curve. Where that line goes straight vertical, that is the highest frequency. That is the FO, the highest frequency of the E layer that you can use for vertical skywave. Okay, not MUF, which relies on your transmission angle, but anybody who's taking a radio transmission and trying to pierce like a needle, pierce through that ionosphere. So where that line goes vertical, that is what is called the FOE for the E layer, right? If we come back down to a real ionosond, you can see it. Here is the E layer, this first one. And guess where the FOE is? Right about here, right? Because that's where it goes vertical. Oops. terrible vertical right there. Okay. Now, jump back over here. Here's FO. This is going to be the height of the F1 layer. So when you get past the E layer, of course, you're going up. Now you're still, the ionosphere is still sending its frequency. It's still going, whoop, it's still trying to send its frequency. And so it pierced the E layer, but now it reaches the F layer. So we get the same kind of thing. Now we're going to get a flattening of that signal. So as it begins to turn it up and go up in frequency, it's still hitting that F layer. It's still hitting that F layer. It can't pierce, can't pierce, can't pierce. And then it starts piercing that F layer. That's the F1 layer. And you start seeing that signal going up again, right? Where it pierces and gets completely vertical. Well, not completely vertical in this case, because it's just the F1 layer, because it's going to pierce now to the F2 layer. But where it pierces up to the F2 layer, where you see it basically going vertical, that'll be the edge, the FOF1. Okay. On this side, if you see, here's the E layer again, and it goes vertical at the FOE. And now you're getting into the F2 or the F1 layer. So now we're at the F layers. And again, you're going to follow, it's a little bit ratty because there's two different waves happening. There's an ordinary wave and an extraordinary wave. They kind of echo and follow each other. I'm not going to go into the details as to why, but it has to do with plasma frequency, ionospheric physics. But you can see pretty flat through here. This is the height of the F1 layer. And then you watch it curve, right? Now we're getting up to a higher frequency. We're beginning to pierce through that F1 layer. And you watch it go up. And where the peak of that is, boop, right there, that is FOF1. Okay? That's the maximum frequency that you can use if you are going straight up, right? It's not the MUF, because that relies on how wide your V is, how your transmission angle. You're looking at the ionosphere from the side, from an angle. You're not going straight up. You're tilting and going off to the side. So your MUF will be higher for F1 than this. This is only if you're going straight up, right? You're dropping the stone straight in the water. You're not trying to skip it across the water. Then, so that's F1. We do the same thing again. Not any more difficult. You start going up in frequency, a little bit higher, right? We're going higher in frequency. You now are in the middle of the F2 layer. Okay, you've pierced that F1 layer. Now you're at F2. It flattens out a little bit, and you keep going higher in frequency. You're going to get to a point where you pierce through that. Your needle will pierce through that F2 layer. And where it pierces that F2 layer, goes off. In a real ionosonde, again, the lower frequency is the one you pay attention to. So you see those two echoes. The extraordinary wave is typically higher than the ordinary wave. So here's where that peak in F1 is, right here. Okay. And you can see a second peak here. That second peak in a little bit more shallower. That's the extraordinary wave. It's kind of an echo. It isn't, but I'm going to call it that for now. So ignore it. It's just a repeat. Look at the ordinary wave, which is the first one and typically deeper. So now we've come back down here. Guess what this is, guys? This is the F2, the height of the F2 layer. Okay, and now we got to get our needle to get a high enough frequency to pierce through that F2. And where do we see that? Here we go, up, 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 up. So right about here, in this case, frequency of 7 megahertz. Okay, so F2 is 7-ish, give or take an ish. Okay, see that? And of course, the extraordinary wave follows it afterwards. This second part over here. And then you get the higher echoes from the bounce, where it bounced off the ground and then did the same process again, but now it's doing it later because it's not really the initial transmission. So this is what ionosondes really look like. Okay, they're a little bit messy. You have to kind of see through echoes and stuff like that. But this is how they kind of work. And then again, dark and dirty, rule of thumb, right back of the envelope. Take your FOF2. Right, that you see, whether it's FOE or FOF1 or FOF2, right? Multiply it by 4-ish. Then you'll get your MUF essentially for 3,000 kilometers in that local area, okay? Or you can look at those other maps, and those will help too. Now, are they going to all agree? Probably not, because these are going to be updated faster, right? Because these are ionosondes that are doing it like every, I don't know, few minutes, right? Some of them I update really quickly. So you can get a lot more local weather patterns and a lot more local, distortions and stuff of your ionosphere, the ionosphere just above that station. Remember, those stations just go straight up. So that's why when you see on these maps, they show, come on, my computer really doesn't like to talk to me very well. Where's the maps? Not you. Let's go down to the map. Yeah. This is why when you look at this map and you see the dot in the middle of the circle, that's where that transmission is. And the radius is showing kind of the effect, kind of where that locale is. Okay. So it can give you, if you're in any one of these circles or anywhere near one of these circles, it will, the ionosons can be very useful. Are they useful for people who are outside of these circles? Yeah, I don't know. Don't know enough about ionospheric physics to know how well people can trust them outside of those circles. But would I say they're useful? Yes. And if for field day, if you can do a dark and dirty and know how to read them, they could be very useful to you. Let's see. Yeah. So again, this is kind of the dark and dirty on how to read them. Read them very quickly. Is just to use this kind of thing and understand that a lot of them will be ugly. They're not going to be pretty. This is an okay ionoson. This isn't a beautiful one. It's just okay. There are some that are so unbelievably messy, it's awful. You can get things like spread F and all this kind of stuff when thunderstorms hit. Inclement space weather can make them look really bad. Here's a couple of examples. I'll just show you this. This was during a solar storm. You can see here's KP for this particular storm back in March of 2017. Here's some ionosons. You can see a lot of the echoes and stuff, but you can definitely see where in this case, I believe this was the F layer in here, and you can see multiple echoes, and you can see how it evolved over time. Didn't really change all that much. That was my point, was during this particular solar storm. Solar storms don't always affect the ionosphere for NVIS very much. Bigger storms, however, do, and I'll show you that in a sec. Bigger storms can affect it dramatically. So if you have a huge storm like the October 2003 storm, you can decimate your ionosphere. You can go from something reasonable with an MUF of in the 20s, 20 megahertz, to an MUF of 9.5. This is for a 3,000 kilometer hop, right? Your FOF2 is way down at 3.2. So solar storms, if they're big and they're long lasting, can affect things. Ionosons often show a lot more disturbances during inclement neutral atmosphere weather. So that can be an issue for you. But again, it's that propagation time to go up. So hopefully a little bit of that helps. I'll take a bunch of questions if you guys have questions about any of this, especially for field day, more interest in ionosons or where to get more of these maps or anything like that. Hopefully this kind of helped a little bit, but I'm not quite sure. I don't know. So let me know how well I do, guys. Huge fan of your teachings. Oh, thank you. Thank you so much. I appreciate that. That's very kind of you. Why do some of the ionosons have two circles? You know what? I don't know. I don't know the details of that yet. That's a good question. I'll see if I can dig more into it. Again, if you weren't with me earlier, my favorite ionoson site went down, and so I had to use my backups. So there's a lot of material in some of these other sites that I am not all that familiar with. Remember, I'm a heliophysics person. I study the sun and the space between the sun and Earth much more than I know ionospheric physics. Ionospheric physics is not my bailiwick. So I am learning at a very rapid rate. And you amateur radio operators have really inspired me to learn a lot more about this particular field. So I'm doing the best I can. Someday, can you talk about LUF, the lowest usable frequency, which depends greatly on transmitting power? Yes, I'll have to learn more about that. That was one of the things I debated whether talking about it. And I said, you know what, I'm not going to, because I don't know enough to feel comfortable talking about it with any or not say accuracy, but any confidence. You'll learn, if you don't know that about me, I have very little ego when it comes to this kind of thing. If I don't feel that I know enough, I'm not going to BS you. I would much rather say I honestly don't know than to try to make up something because I want to look smart. I don't need that stuff. I want to give you guys the right information. So I'll need to learn more about LUF to understand it better and give you a better idea. Clearest explanation of ionosons I've ever seen. Oh, good, really? Finally, I feel like I understand them after about 35 years. Wow, Stu, thank you. That just floored me. I'm like weak in the knees right now. Thank you so much. I thought I totally bungled it, so I appreciate that. They're really not that hard to understand when it's the simple stuff. I mean, when you start getting into spread F and all that other stuff, it can get really crazy. And I've got a lot to learn when it comes to that. But at least for right now, because the space weather is calm, and I think the terrestrial weather isn't too bad either in many areas, I think a lot of the ionosons will behave themselves. So thank you for that. I learned something from you every live stream. Thank you and all your supporters. Oh, I appreciate that, Noah. That's kind. Yes, I am very grateful to my Patreon supporters for that. They're wonderful. They're my family. Tamitha, please show a list of your URLs used here, and we will go look later and get it understood. Yes, what I will do, Glade, is I will put these links that I've up. As a matter of fact, I'll put them up again right now. You'll have to, look at them from this perspective. Sorry about that. But what I will do is put them in. If I can stand out of the way, no, stand on the side. I will put them in the description as well. And again, my favorite ones are these two up at the top that are not lit up in blue. These are my two favorites, but both those sites as of last night and earlier this morning are down. I don't know if anyone's checked them. PropQuest isn't down, but the FOF2 stuff and the MUF stuff is down because I think he uses Giro data. But the Giro site has been down, and I'm very upset about that. The entire UML site has been down. So uml.edu is out, and I don't know why. I think is it Madison or Massachusetts? I can't remember off the top of my head. But the whole institution is down. I have no earthly clue why. But yeah, those are let me stand again out of the way. Those are the websites to go to, at least for right now. The ones that are in blue, that'll help you a lot. Okay, let's see. Thanks, you're great. Oh, you're welcome. We all love you. Oh, I missed one that went up off the top. Excellent information. I have watches solar forecast when it concerns solar storms, so the extra information is very good. Oh, excellent. I'm so glad. From the UK, thanks for a great explanation. You're very welcome, Mark. Yeah, it's late there for you, isn't it? So thanks for staying up with me. Chemtrails killed my rabbit. Very cute. Is the max frequency you can send the maximum supported frequency sine of the antenna angle? It's measured to the horizon. It's actually the cosine. It's the cosine of the angle. So it's the angle it's going to be the part of that transmission that is parallel to that layer, not perpendicular to it. And if you're looking at the incident angle, which is defined from the layer, it's actually the secant, or the 1 over cosine. And so I didn't get into the details of that, but yeah, it's the cosine of the angle, right? It's not the part of the needle that pierces through. It's the part that is parallel to that layer, and that will be from the way the transmission angle is defined. It's going to be cosine. It's going to be the part that's parallel to the ground. Okay, so and again, that all depends upon how flat your layer is, right? We talked about if that layer is warbling back and forth, then that perpendicular to that layer is also warbling. So that's where weather effects and local effects become problems, especially if you have lots of gravity waves. If you ever notice you're having trouble getting decent transmission, and you look up and you see lots of, Kevin Helmholtz type of ripples in the sky with these clouds, a lot of ripply cloud formations, you'll be like, oh, there may be gravity waves propagating up to the ionosphere, and that may be causing those layers to really look like this a lot. And that can give you problems with radio propagation. These are what we call ionospheric disturbances, or TIDs. And that happens a lot with tornadoes and had big hurricanes and rain, big thick thunderstorms and cyclones, things like that, as well as space weather. So, okay, let's see. In Massachusetts, Lowell's, yeah, it's the Lowell's did base, yeah. It's been down for a couple weeks with IT problems. Thank you, InfoDog. Thank you. I've been wondering what's been going on. I hadn't checked it in a while, and last time I checked, it was obviously more than a couple weeks ago. It was up with no problem. So it's horrible that it's down right now with IT problems, because it's just such a fantastic resource. So I hope they get it up soon. Cheers from the Ukraine. Thank you. I appreciate that, Levets, if I'm reading your name correct. Lazovets. Thank you so much. I'm glad to have you with us. I've been using, Andy, of course, you've been using PropQuest for years. I'm so excited. I get to meet Jim Bacon next year at HamSci. We're both going to be giving, I think, back-to-back talks. So we've both been asked to give tutorials. And I think it's Jim's first time coming to the United States. So it'll be fun. I love his sense of humor. So I can't wait to meet him in person. You're welcome, Paul. I'm so glad. Hopefully, and I'm of course I'll share anything I can do to help out, especially with field day. So yeah, Florida's. I agreed. Good luck on field day, guys. And you're so welcome. You're so welcome. So now that you have a call sign, we will hear you on the air. Yes, I'm getting there. As a matter of fact, I'm going to be with my Elmer tomorrow. We're going to go to several local places here in the Valley and just say hi to people during field day. So I get a feel for what field day actually feels like for the first time. It'll be really a lot of fun. I try to read these graphs and I'll give reports in my prepping community. Good. I suck. Yeah, well, join the club. I suck too. I am definitely not an expert. But as you can see, even I'm able to read them. So, you know, and we're able to kind of talk about them a little bit. So when the ionosons are well behaved, don't expect to be able to read them all the time. But even just that little bit of information should help you get through them when they're reasonably well behaved. And even when they're not well behaved, that at least will tell you that either something's wrong with the ionoson or digisond, or something is just really terrestrially or in those layers, something is really crazy, and it probably will you know, there's a good chance that it will reflect in your DXing. So that's one thing, is that when you're armed with that kind of information to be able to read these types of plots, it arms you with another tool to be able to say, you know, is it my rig or is it the weather, right? And that's always got to be a good thing, because the last thing you want to do is sit there and start unplugging wires and trying to troubleshoot something when it has absolutely nothing to do with your equipment. It has everything to do with either the layers because of terrestrial weather or space weather. So the more tools I can give you to help you understand that type of thing and put them in your arsenal, the happier I am. So why do VLF signals get enhanced during a solar storm? Oh my goodness. Well, that's the same reason why HF signals get enhanced during a solar storm. You get more, a lot of times you get more ionization in the upper atmosphere, especially on Earth's day side. Night side, there's so much disturbance going on with the magnetic field, it just trashes HF a lot of the time, especially if it's a big storm. But then also you get auroral propagation. You can get, you know, both in VHF, actually VHF repeater people have talked to me and told me that they notice it. A lot of that, of course, the handheld people don't notice it because they don't see what's going on behind the scenes with the repeaters and people trying to squelch the noise and all that kind of stuff. But you can get auroral noise on VHF. Absolutely you do. But in HF, of course, you can use, like on 6 meters and 10 meters, a lot of times you can get auroral propagation that you can then use as another layer. So, you know, even radiation storms to some degree can create sporadic E. As a matter of fact, in, what was it? I think it was the 1972 storm. There was reports that there was a sporadic E layer for HF that had been created because we had a Carrington class event hit, and it actually created a sporadic E layer almost all the way across Russia that people were using to do HF propagation. So even radiation storms can be beneficial, sort of, depends, you know, how bad they are. It's a real mixed bag, but that's why. It's because it's playing with the ionization in the upper atmosphere. KP index and effect on human health. Yes, right. There's lots of health aspects, and that's more to do with the geomagnetic field, but there are some people I'm learning who have sensitivities, maybe chemical sensitivities to to radio bursts as well, very much like some animals do. They have sensitivities to that. So geomagnetic field changes and meaning the Earth's magnetic shield wiggling, and then radio bursts at very high frequencies can cause problems. Just like, cell phones, holding them up to your head, for long periods of time, people get cancer from that, right? And so radio bursts can do the same kind of things, because these are really intense radio signals, and people who are super sensitive to it have indicated they have issues. But that's a field that has, oh my gosh, it's probably decades off from being really well developed. People are hardly understanding that stuff yet. Bart, let's see. Thank you. I always learn so much from your lectures. You not only answer questions I have, you also challenge me with new things. That's great. And I never would have known to ask. Ah, that's so cool. You hope to be at a Papa meeting soon. Good. Please do. Yes. And then ask me questions there. But yes, Bart, thank you so much. I mean, you are the whole reason why this has now turned into like its own mini course as it is. I might even like change the title on this at some point and add it to the freeform mini course side of things, because you guys have kept me on for almost 2 hours. So it's I love talking to you. I love being able to answer questions and help as much as I can. So, okay. Oh, thank you, Studio A. Please do leave your like so we can help YouTube algorithm to recommend my content. Thank you so much. That's so kind of you, Studio A. Okay, guys. Yeah, go get ready for field day. My goodness. I mean, we've been on for a long time, but hopefully this is good stuff. And please feel free. I'll keep it up. Feel free to refer back to it later. And hopefully, and just know that when we get to the point in the second chef course set of courses, when I go into the ionosphere, we will revisit ionosons, and we will do this in a much more detail. And I'll see if I can get that answer about LUF at that time. I hope I can. We'll see. But I'll know more than I know now, and because I'm constantly trying to learn more. And hopefully these the GIRO site will be, the Lowell data will be up and running again. Okay. All right, guys. I think that's it. Any other final questions before I go? What is field day? Yes, people are going into the field with radios. It's a huge thing. It's happening all over the United States, and actually, I think a lot of people do it all over the world because it's such a big deal. And it helps with all the emergency responders, helping them keep their chops up, and helps with people in the military as well. There are lots of different things that people do as first responders to help ensure that they're ready to respond on a moment's notice. So people who participate in field day, these are the people who are keeping the rest of us safe when there are big emergencies. Big disasters like hurricanes, like earthquakes, like things where I don't even want to talk about terrorist attacks, but things where systems, big infrastructures go down, and there's no other way to communicate other than HF radio, or there's very little in the way of communication other than HF radio. And these people step up out of the goodness of their heart, and they serve and protect all of us. So that's why I really enjoy doing these types of things and serving the amateur radio community. You guys you honor me just by your existence. So I'm very, very pleased and very proud to be part of your community. And yeah, I'll leave it at that. Okay. I think that's it, guys. So yeah, love it. See, people do get headaches. That's a classic thing. Headaches, tinnitus, migraines. That's very common, and just general malaise. Especially if you have heavy metal poisoning, you could be susceptible. If you have plates or screws or medical procedures where they've left metallic objects in your body, rods, pins, that type of thing. Anything that would prevent you from going into an MRI, for example, without having problems, that can make you geomagnetically as sensitive to space weather. And that is something that I've seen. Between that and people who have heavy metal poisoning, like mercury poisoning or cadmium or chromium, any of those heavy metals, obviously lead poisoning, those people are sensitive as well. They're really sensitive to electromagnetic fields. So those are the parts of the population that I've seen the most have issues with space weather. But there are others as well. But yes, so you're not alone. You're actually part of a growing community, because as we tinker more with human anatomy and turning us all into cyborgs. People themselves are becoming more space weather susceptible because we have more body parts in us that have technologies in them that are susceptible to it. Strange, isn't it? Yeah. Anyway, sci-fi becomes sci-real. Okay, guys, I think that's it. And have fun. Have fun on field day and do DX. And the weather looks good, so enjoy. Okay, and I'll talk to you guys soon.